Hello there. In this video we're going to be discussing some properties associated with parallel and perpendicular lines. So in short, parallel lines are lines for which have the same exact slope and never intersect, and also perpendicular lines are ones that intersect, but they intersect particularly at a right angle. So we're going to describe a couple properties associated to this. We're going to prove formally the theorem associated to parallel lines and their slopes, and also do a couple examples on how to find equations of lines that are parallel or perpendicular to lines of interest. Alright, so let's formally state the theorem associated to parallel lines. So if L1 and L2 are parallel, then the slopes M1 is equal to M2, provided that their vertical intercepts B1 and B2 are not equal to each other. So let's consider the special case of where B1 actually is equal to B2 and M1 is equal to M2. So if that is the case, so if you have one line here and they have the same exact slope, so they increase or decrease at the same exact rate, and they cross at the same exact point, then the only way that that can be true is if L1 and L2 are precisely equal to the same line. And some people refer to this as collinear lines. That is, lines are pretty much represented by the same exact graphical shape. So how can you prove this formally? So L1, let's assume, has the equation y is equal to m1x plus b1. And line 2, let's assume, has the equation y is equal to m2x plus b2. So let's assume these are two lines in a plane. So if they have the same exact points, then that means these two equations are precisely equal to each other. Or we want to know or prove that these two lines never or always intersect. So set equal to each other to see when they cross, if ever. So if that's the case, we have m1x plus b1 must be equal to m2x plus b2. So if that is the case, let's use our assumptions that we have that m1 and b1 is the same as m2 and b2 respectively. So that means m1x plus b1 must be equal to m1x plus b1. And this is only by assumption that the slopes and intercepts are the same. So if that's just the case, if I subtract b1 from both sides of this equation, then those are going to cancel. So I have that m1x must be equal to m1x. And if I subtract m1x from both sides, then this is going to give me the statement that 0 is equal to 0. So this is going to be always true for any x for which you choose. So if this is true, then that means they're always going to be equal, which implies that the lines are collinear lines. So that's the special case of this theorem. So let's consider case 2. Let's consider the case where m1 is equal to m2 and b1 does not equal to b2. So this is the case where they are not collinear, so our goal is to see if they are parallel or not. So again, we have two lines, line 1, which is y is equal to m1x plus b1, and line 2, which is y is equal to m2x plus b2. So we're going to set these two equations equal to each other and see if they are ever equal to each other. So if that's the case, then I have that m1x plus b1 must be equal to y is equal to m2x plus b2. So we're going to assume that m1 and m2 are equal, but b1 and b2 are not. So if that's the case, that means m1x plus b1 must be equal to m1x plus b2. So this is by assumption that m1 is equal to m2. So if that's the case, I'm going to subtract m1x from both sides of this equation. So this is going to give us that b1 is equal to b2. So this is never true if b1 is equal to b2. Never. So if these two things cannot be simultaneously true, then that means there does not exist an x such that the lines cross, which by definition is what we call parallel lines. So that means two lines are going to be parallel if their slopes are equal to each other. Alright, so if that is the case, let's assume case 3. Let's assume that m1, m2, b1, and b2 are, can be whatever they want to be. So again, I'm going to consider my two lines, L1, which is going to be y is equal to m1x plus b1, and line 2, which is y is equal to m2x plus b2. So I'm going to set these two equations equal to each other. So I'm going to have that m1x plus b1 must be equal to m2x plus b2. I'm going to start moving stuff around, so I'm going to subtract m2x from both sides, and I'm going to subtract b1 from both sides as well. So they cancel and those cancel as well. So I get the equation m1x minus m2x is equal to b2 minus b1. So I'm going to factor out an x out of the left-hand side, so I have x times m1 minus m2 is equal to b2 minus b1. And if I solve this equation for x, then that means x must be equal to b2 minus b1 all over m1 minus m2. So the lines will cross. So case 1, lines will cross if m1 minus m2 is not 0. Because if that is not 0, then that means m1 minus m2 is a particular number, like 5 or 6. b2 minus b1 can be equal to 0 if they want. They can have the same vertical intercept, because 0 divided by something is still 0, so that's perfectly legitimate. So the lines will cross if m1 minus m2 does not equal to 0. And if m1 does equal to m2, forcing the bottom to be equal to 0, then we have a couple cases here. So if b1 is equal to b2, then we say the lines are collinear. And if b1 does not equal to b2, then we say that the lines are parallel. So these are the three possible cases that are associated to linear equations or lines in the 2D plane. So let's do a couple examples on how to construct particular curves or lines that satisfy some criteria that we want. So find a line parallel. Find a line parallel to L1, 3x minus 5y is equal to 7, that passes through the point -3, -4. So solution, let's consider line 1 here. So 3x minus 5y is equal to 7. I'm going to isolate this equation, so I'm going to subtract both sides by 3x. So I get -5y equals -3x plus 7. Then I'm going to divide both sides by -5. So I get the equation y is equal to 3/5 x minus 7/5. So this is line 1. So if that is the case, then that means slope 1 is going to be equal to 3/5. I want these two lines to be parallel to one another, so that means m2 must have the same slope as m1. So that means that has to be 3/5 as well. So that means line 2 is going to have the equation y is equal to 3/5 x plus b. I don't know exactly what b is, but whatever b value it has to pass through the point -3, -4. So let's figure out what b makes that true. So if that is the case, combining these two assumptions, I have -4 is going to be equal to 3/5 times -3 plus my unknown value of b. I'm going to multiply my numerators together since that's just over 1. So I have that this is going to be equal to -4 is equal to -9 divided by 5 plus b. I'm going to add 9/5 to both sides. So b is going to be equal to 9/5 minus 4 over 1 times 5, top and bottom. So 5 times 4 is 20, and 9 minus 20 is going to be -11. So this is going to be a -11/5. So that is going to be my vertical intercept for my second line. So that means the equation of the line that I want is going to be equal to y is equal to, what was my slope? 3/5. So 3/5 x minus 11/5. Now, if you want this to be in standard form, we can begin by multiplying both sides of this equation by 5, if you don't like fractions. So we get that 5y is going to be the same as 3x minus 11. And I can subtract 3x from both sides, so we can rewrite this as -3x plus 5y is equal to -11. And if your teacher or you don't prefer that leading coefficient to be negative, we can rewrite this as 3x minus 5y is equal to 11. So this is an equivalent representation for line 1 that satisfies the characteristics that we want. Alright. So in the last video we also proved using some trigonometry that if line 1 is perpendicular to line 2, then the slopes of line 1 and line 2's product must be -1. That is, they are negative reciprocals of one another. So if you're interested in that proof that you haven't already found it, please check that out. So if my first slope is 7/5 and line 1 is perpendicular to line 2, that means the slope of the second line must be equal to what? So the negative reciprocal of 7/5 is going to be -5/7. So let's work through an example of constructing a line that satisfies properties. So find the equation of the line perpendicular to L1, which is given by 2x minus 3y equals -5, that passes through the point 1, 2. Alright, solution. So let's look at line 1 to start. So 2x minus 3y is equal to 5. So I'm going to begin by subtracting 2x from both sides of this equation. So then I get that minus 3y must be equal to minus 2x plus 5. I'll then divide both sides by -3. So I get that y must be equal to 2/3 x minus 5/3. So this is the alternative slope-intercept representation for line 1. So from its representation we can find that slope 1 is equal to 2/3. Alright, so what do we know? So since we want L1 to be perpendicular to L2, then slope 2 must be equal to the negative reciprocal of 2/3, which is -3/2. So that means our equation for line 2 has the following structure. Y is equal to -3/2 x plus some number b. And we want this line to pass through the point 1, 2, so that's going to allow us to find this b. So that means 2 must be equal to -3/2 times 1 plus b. So I'm going to add 3/2 to both sides. So b is going to be equal to 2 plus 3/2, which is the same as 2 times 2 is 4 plus 3 is 7 over 2. So if that is the case, then that means line 2, that satisfies our given condition. So perpendicular to 2x minus 3y equals -5, passes through 1, 2, is given by the equation y is equal to negative 3 halves x plus 7 halves. So if you want that in standard form, you can multiply both sides by 2, so 2y equals minus 3x plus 7, and add 3x to both sides, so 3x plus 2y equals 7. So that's the standard form of the second line of our interest. So this is just some examples associated to finding equations that are parallel and perpendicular to particular lines of interest. Hope you enjoyed.